I just exit that one. We are to see how we can extract data from a case down to simple files, which then can be copied into Windows and plotted in MATLAB, for instance. So how to do that? Well, here I start by locating OpenFOAM. So you can use this folder as a starting point and then just go to parent, 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 all the way down to the root on your memory pin on your system. OpenFOAM is located under opt folder here. So I double click on opt and then OpenFOAM. And then we have a folder called documentation. Doc for short. And inside that one we have, come on. We have something called guides, and here we have two PDF files, one for A4 and one for US letter. Of course we choose A4. Here we have the only documentation that we can get for OpenFOAM. So this one is something that we will have a peek into. It's many pages here, so we don't need the first one. They are quite boring. A lot of trademarks and license and everything, nothing to worry about. So here you find listed the different tutorials, lid-driven cavity flow, and how you can play around with the mesh, how you can play around with ParaView, how you can use it. So yes, quite interesting. Next test case here at next tutorial, that's solid mechanics, so we'll skip that one. Breaking of a dam, something we have done. We're going to look further into that one a little bit later. Then more theory around OpenFOAM, applications and libraries. So here you have a lot of utilities. And then here, OpenFOAM cases, a little bit in detail. We are going to address some of this, but not now. Chapter 5, that is a little bit detail how you play around with meshes. And finally, chapter 6. Here is something interesting for us. It's a post-processing tools. Now, for those of you now who has the old version of OpenFOAM, this doesn't work, what we are about to do. Previously we had some other program. Here we are going to peek into something called sampling and monitoring data, chapter 6.3. So here we have options how to extract data from a case. Probing data, probes, not so interesting. Then you have certain monitor points where you want velocity, pressure. What I want is sampling for a graph. So we have something here called a single graph, and that is something I want to use. So how to find this one, how to use it. For this tutorial here, they have used as an example the PITS daily test case. Now I don't have the PITS daily test case in my run folder. I only have the cavity case. So I start by copying the PITS daily. That was under open foam, tutorials, incompressible, and then it was simple foam. And here I think it was PITS daily. So I just run this one quickly, block mesh, and then it was simple foam. So this is the PITS daily case. Takes a little time to run. Here. So now I have some results, and what I want to know is, or actually what I want to do is to include this single graph file. So we have to find that one and copy it into the correct folder. So what you then can do is mark this sentence like that. You just left click and drag, and then you can mark a text, and then get the terminal in front. And if you now click the mid button on your mouse, he will paste the entire string, command string, in one sentence. Then you don't have to write it, and then just hit enter. And then he copies this single graph file into my system folder. So if I now write ls system, I will have a single graph file lying there. That one has to be modified. So I start my editor, GENE space system, and then this single graph file. So it looks something like this. This is sort of the default that is with the distribution, and he has some very strange locations there. You specify the start and end position of a line, and then you want velocity and pressure along this line. So the starting point here, it's definitely not the original values here, so we have to change it. This is what it should look like. So again, you can use, just mark it, and then back here you can use the mid button. Ah, I missed. Undo. Should be here. Not easy. Ah, I'll write it. Not that complicated. It should be, what was it? 0.01, 0.025. 0.025, and the set position should be 1. For the endpoint, same numbers, only with a minus. 0.01 and then minus 0.025. That's it. Save this file. And then one more step to make this work. Inside the control dict file, that's the sort of the major file, the important file that actually runs or is in charge of the entire case. Come on, he's slow. Open the control dict file. Here we have the control dict all the way at the end. Come on, thank you. He has include function streamlines. That's the default for this Pitts-Daly case. I don't want streamlines. I want the one that we just created, and that was single graph. So I remove streamlines and I write simple graphs instead.
Is it single graph?
Thank you. Single graph. It was single. Single graph. That one should be okay. Yep, looks okay. So now we save this one, and I try to exit. Quit. So now I should have control, back control to this one. Now I have already run the Pitts-Daly case, and he gave me a folder called processing. But I want to destroy everything now except the initial files. So I want to remove this post-processing folder. I need rm minus r, like that. And then I run the case again. Simple foam. He crashed. Something is wrong here. But I'm monitoring runtime. Okay. Oh, he worked. So now, yes, I get the same results. He's finished in 298 iterations, and I have a new folder now. The one I just destroyed is called post-processing. So now I want to have a look what's inside there. So let's have a peek. I can go to my home folder. Where are we? Home folder? No, bad idea. Where are we? Run folder. No, that's the wrong one. Where the heck are we? Open foam. There we go. Run folder. Pitts-Daly. And then under post-processing, you have single graph, and there you will get one folder for each of the times of the here it's a steady state code actually, so it's just an iterative method. He used time as an iterative dimension, but he saves the results for every 100th of a time step. Of course, I'm only interested in the last one. And then finally, you have two files here, and I want to inspect the velocity. So here you will have just a data file. The first number, that is the position along this line that you have specified, the starting point and the end point. So he starts with the position 0, that will be in your endpoint, and then he goes all the way up to the maximum, and here it was 0.05. If you can recall, the starting point was 0.25, the ending point was minus 0.025. So the total distance, yes, it's 0.05. So that's the first column, then position, then the 3 velocity components. Velocity in the x direction, velocity in the y direction, and finally the velocity in the z direction. You see the velocity in the z direction is not completely 0, so he still uses this equation, although it's a 2-dimensional case. Now this one can be plotted using here, for instance, what have they used here? GNU plot, yes. Or you can copy this file onto your hard drive, or if you don't want to touch your hard drive, you can copy it into your, if you have a memory pin, an additional memory pin, you can copy it out there. If you want to copy it into your hard drive, then you have to, well, not that one. Double click on it. Ah, it doesn't like it. Something wrong with my hard drive here. Doesn't look too good. So anyway, it's just a plain ASCII file, so that one can be copied around. And loading it into MATLAB, we'll see how that is done later. You just actually write load and then the file name in MATLAB. Then he will load the entire content of that data file into one single matrix, and then can easily be plotted. So that was sort of the recipe how to use a single graph, how to obtain, say, a velocity profile along a line inside a domain, or the pressure distribution for that matter. Any questions to that one? That's okay. Okay, we have some more time. Let us skip this one. And this one. And this one. I go back to my run folder. And I want to use this dam break case. I want to play around with that one. Now we have run dam break once. We can take a quick repeat for that one. Dam break text. Come on. Here we go. So these recipes, they are not entirely correct. They are based on an older version on OpenFOAM, so don't pay too much attention to the details in it. Start by copying this test case, this tutorial, and it should be located under multiphase and then interFOAM. So let's see if we can find it. Tutorials, and then it was multiphase, and here it was interFOAM, laminar, and dam break. And then another dam break. Change directory to dam break. So here you have the entire case for a dam that should break. We start by creating the mesh, block mesh. That's done. Then we have something that we have to do here. We have something called an alpha I think it's fixed already for us. So let's just try to run this interform directly. Interform and then paraform. Here you have to scroll down and choose this alpha.water. He has to be included and then apply, because I want to plot this alpha factor. No, it didn't work. Okay, I had a suspicion. Okay, then we have to exit, and then we have to, what do we have to? Inside this 0 folder, ls-l0, we have some files. One is called alpha.water, another one is called alpha.water.original. And what he does is to specify where should, in this domain, where should we have water, where should we have air. And to do that, you have to use something called set fields. Let's see if that one runs. Yeah, should be okay. Set fields. He has now, should have at least created water at some location, and then we can run again, interform. He should overwrite all folders, and then paraform again. Cross-eye for the alpha.water, apply. And yes, there you have the initial state. The red one is a block of water, the blue is air. And then when we let the dam break, the water should slosh over the small dam down here. So that is the dam break case. Now I want to run this case again, but I want to do it with 2 CPUs. I want to run this case in parallel. So that should be possible. How many CPUs do you have? When you bought your computer, the sales guy, he said something, very big number. You have 20 CPUs on this PC. It's a very good PC. And that's a big lie. If you want to know how many you have, you write ls CPU. Then you have a lot of information about the hardware. And you see on this computer here, I have 8 CPUs on this one. Does anybody has more CPUs than me?
What did you write? LS?
LS CPU in one word.
In one word?
4, yeah, it's a cheap one. So it's dependent on the hardware, how it's organized, so how many cores you have, how many threads you have, and what they call it. But this is the number of CPUs that OpenFOAM can actually access. So I can split a case in 8 parts and use 8 CPUs. Then hopefully the total simulation time should go down substantially. That's the philosophy here. Okay, but the recipe, how this is done, you will now find, if you look at this PDF file for the dam break case. So first, it's just a traditional 1 CPU run. So don't mind that. But here you have running in parallel. Little description about how it's run in parallel. So here they start by suggesting you clone the dam brake case to another one. Here I don't care if I destroy the case, so I just use the original. It really doesn't matter. Then you have to find this decompose par dictionary file and change it. So let's see if we can find it. I have a text file here, so if we now just open, let's see if we can find it. User, open phone, run dam brake, and then inside the system folder. That was wrong. Open system, decompose par dictionary. Here we have it. So here the default, he has suggested to split the domain in 4. I want to have only 2. Simple method how to split it, and not as he suggests here 2 by 2 by 1. I want to have 2 by 1 by 1. So now I should have split this one in half. So we save this one. Then we can execute decompose par. So we try that, decompose par. Let's see. Now I am inside the dam brake folder. I want to destroy all these result files except 0. I want to destroy all the files as if I haven't run. So how do I do that? Remove -R. And then I remove all files starting with 0 dot star. That should remove all result files. Also number 1. Let's see if this works. Yes, I have now removed all the result file except the one just called 0. That's the initial one. I need that one. Then we write decompose par. Decompose par. Decompose par, he should take my setup, the entire case, and copy it, sort of split it into CPU 1 and CPU 2. Or actually, he used it as processor 0 and processor 1. So now I have split it in half. And to run it, you have to use this MPI run minus and so on and so forth. So let's try that one. MPI run minus number of processors. MPI run minus number of processors 2, program interphone minus parallel. So now he should run much faster if he wants to start. Thank you. Now he uses 2 CPUs. I mean 1 CPU versus 2 CPUs. Should it will not be half the computational time, but smaller. We can check it afterwards. Here he used 4.73 seconds. now you have the results, but you don't have the result as you're used to. You have two separate result sequence, one from each processor. And actually it's possible here now to just look at one of them if you want. So let's see. Where was it? Just reconstruct. Should be here somewhere. Let's just try it. Para foam, or actually para view, I think it is, minus case, say processor 0. Let's see if he can handle it. No, he didn't get anything. Let's try to open one. No, he doesn't get it. It should be possible here to take just one case. Let's try with parafoam instead. Yeah, there you have it. He actually only reads half the case. So it looks very strange to only get half of it. So in order to get the whole thing, exit this one, and then you have a program called reconstruct pod. It was reconstruct pod. He will then take the parts and join them together in, no, not reconstruct part. Wasn't it reconstruct part? Reconstruct.
Minus a K.
Ah, yeah, he doesn't like the K. There we go.
When it's something that both CPUs work together.
Sorry?
When the problem is being solved, then the CPUs are some kind of conflict.
Yeah, I mean, if it's done well, if it's programmed nicely, then splitting it in 2 or 4 or how many processors you have should reduce the CPU time, the overall simulation time, with, say, the number of processors. That would be ideal. But of course you have some overlay because they have to talk to each other during the simulation. Like in this case, we split it in half. Then of course, if something flows out of the one calculation, it enters into the other one. So this information has to be sort of, they have to talk to each other during the entire simulation. So you have some overhead. So of course it doesn't scale perfectly, but OpenFOAM has been programmed very well, so it scales quite good. So with 2 processors, you don't half the CPU time, but well, we can try it. It was 4.7 seconds. So now if I just remove again everything, 0 dot star, oops, 0 dot star, I need rm minus r, and also the 1 folder, like that. Now I'm back to the single system here, and I just write what was it? It was Interfoam was it? Yes. Interphone. Yeah, 6.7 seconds instead of 4.7. So it's not so stupid. Linux is a good operating system using more than one CPU. So if you have many CPUs, 16, 32, hundreds, I don't know, then this program will scale quite nicely. I know they tried with Windows, not Windows 10, but some versions ago. They tried using parallel with Windows. And when they use, I think they tried with 8 CPUs, he used more time than with one single CPU. So Windows is terrible, awful. It can't be done run in parallel, at least not now. It might be better, but in the future. But no, it's not good. Yeah, but with Linux, no, that's a beautiful program. It scales quite nicely. Of course, for us, if you are running on your laptop, it's a limited number of CPUs you have. But we have more powerful workstations, at least in our department. And if you really need a big problem, then we have a supercomputer down here with how many CPUs? 1,000 CPUs, something like that. So if you have a very big problem, oh yes, then you need access to these supercomputers. And they have installed OpenFOAM there, so yes, it's possible to use them for you. So think about that if you really need some CPU power. Okay, that was the demonstration that we had for today. Tomorrow I will start peeking into the theory behind finite volume, looking into the book by Versteeg. So that should then be a sort of normal lecture. I will find the files, the text for exercise 3 and put it out, hopefully during this evening. Any questions? Then we stop here.